One of the themes of this semester has been understanding why chemical reactions occur and potentially controlling those reactions to cause ones we want to occur to happen more easily or prevent ones we don't want to occur from happening at all. To do that, we looked at state functions like Gibbs free energy and path functions like reaction rate, and we were ultimately really interested in conditions like temperature or concentration and how those can inform the outcome of a chemical reaction. In most of those cases, though, we were kind of fundamentally limited in terms of what could occur. That is, if something was not spontaneous, was not favorable, happened slowly, we were kind of out of luck. Now, in my own research, an example of one of those reactions that just really doesn't want to happen would be the transformation of water and carbon dioxide into some kind of energy-rich fuel source. In the case of plants, that's often things like glucose and some oxygen gas. In essence, photosynthesis. Based on what we've seen so far, that process should be both very slow and very unfavorable. It just doesn't seem to want to happen. We're now going to learn about photochemistry. That is, how to do chemistry with light. And in doing so, what we're going to see is that photochemistry gives us a tool to make impossible processes not just possible, but maybe even easy. Let's look at how that works. To do that, I'm going to be symbolizing light in a reaction with a wavy arrow, because of course light is a wave, and h nu written on there. Recall E equals h nu is the equation from quantum mechanics that tells us about the energy carried by light based on its frequency. So, with that prefaced, how does this apply to a chemical reaction? Well, let's look at a potential energy surface. And in particular, we're going to look at a potential energy surface for some process that's pretty unfavorable and slow. Something perhaps like photosynthesis. So our reactants are down in this well. The activation energy is enormous, and even if it could get over it, the products are at higher energy, so the equilibrium is not going to favor them. What can we do? Well, if you recall, back in Chem 103, we drew a lot of diagrams where light came in to something like an electron at one energy level, and when light hit that electron, it went up in energy to some new level. Photochemistry is going to be doing something very similar. If your molecules or catalyst can absorb light in a productive way, that can raise your reactant molecules up to some new energy. We'll call the energy of those new reactants, or the new reactants plus light, R star. From this new position, we've now literally been moved to a different potential energy surface. We're not even on this same surface we were before. As a result, we're not even worried about that barrier that was there previously. We've been raised up in energy so much that now the reactants can basically fall down into that products well. That means that we wind up having a reaction equation where, in a sense, light appears as a product. Light appears as a reactant. That means that light, as a reactant you can add more of, is something that can shift your equilibrium. It can do that because of the energy of that excited species versus the energy of the normal reactants. Now, sunlight is one approach to doing photochemistry, but sometimes it just means shining a really big light or a laser on your reaction as well. Light, in a sense, functions like a catalyst in that it is something that can be added to a reaction to open up a whole new pathway. But it also functions a little bit differently because light energy is being consumed to make the reaction happen. In a sense, it does still appear in the rate law.